Good afternoon. It's 12:20, and so it's time to start our Tuesday Titan talk. Today we've got Professor Susan Sanchez talking about a data farmer's almanac. Susan is pretty well known in the simulation community, and I'm very honored to have to be able to introduce you for this Titan talk. Her history within the simulation conference goes back quite a bit before mine, and I know just this last Sunday she again did the data farming workshop. Susan comes from the Naval Postgraduate School, the Graduate School of Operations and Information Sciences, as well as the Graduate School of Business and Public Policy. She's also the co-director of the Seed Center for Data Farming, has numerous awards and articles that she's written, over 80 publications in the areas of design. I know that me personally, I have done a lot of simulation models which involve kind of the topic which she's talking about, where you've got a lot of just a massive number of inputs that go into a very large-scale optimization, kind of a simulation optimization problem, and it's difficult to know exactly how to weed through that data. And so I'm very interested and privileged to kind of hear how she's going to talk about that. So with that, let's give Susan a nice welcome.
All right, I hope I'm all mic'd up and good to go. And first of all, thank you so much, Steve and Todd, for giving me this opportunity. It's really a thrill to be able to be up here and talk to the Winter Simulation Conference community. So there have been a lot of wonderful talks at the conference so far. We've got a mix of technical talks, application talks, the cross-fertilization tracks that are bringing in new ideas to this community. And I'm going to give you a talk that's not technical at all, but I hope it is something that fits in with the theme of simulation and service. And as the title says, I'm going to look at the Data Farmer's Almanac. And here's an almanac, the one that's been going for a long time, and its motto at the top is useful with a pleasant degree of humor. So I hope by the end of this hour, you will say, I learned something useful or thought of something useful, and yeah, this was fun. So what is an almanac? An almanac has a lot of things. It has some facts, some history, some advice, some quotes, some puzzles, a variety of things. And what I want to do in the next bit is go ahead and change from the old Farmer's Almanac, founded in the 1700s, to a Data Farmer's Almanac. So I'm going to change the timeline from one of the specific farmers to one of simulation. And I'm going to change the categories a little bit, but keep with the spirit of some of those. And as we look at, for starts, December 13th, 2016, 8 days till winter begins. And it's actually 2 days since WSC 16 began. So if we look at some other forecasts, you know, WSC doesn't always do a great job of simulating winter. We've had some recent ones. We did have a lovely trip to Germany with the snow, but often we end up in places that are, well, maybe a little bit warmer. For the current simulation conditions, we had a big wave front move in to Washington, D.C. just a few days ago. The 4-day forecast at that time for winter sim is fantastic. We learned at the opening session that next year we're going to find out the long-term forecast for 2057. So I'm looking forward to Barry's wisdom on that. And I'll have a few thoughts perhaps that I can share with you about what might be coming up in between those two times. So words of the day: data mining and data farming. And when we look at the real world, we see that miners are those that go ahead and seek for treasure that's buried somewhere out in the geography. They may not know exactly where it is. It may not always be easy to find or separate out. And similarly, data mining seeks valuable information that's buried within massive amounts of data. So data mining is just very well known these days. Data analytics seem to be taking over the world, and that's a good thing, I think, for our community as well. At the Seed Center, we like to contrast data mining and data farming in this way. Our metaphor for farmers is that farmers actually cultivate to maximize their yield. So they don't just accept what's out there in their environment, they go ahead and manipulate it to their advantage. They might use pest control, irrigation, fertilizer, different types of seeds, different types of soils. And we do try to stay away from the fertilizer analogy too much. But the idea is that data farming is a way that we are going to try to manipulate simulation models to our advantage. And both data mining and data farming can generate massive amounts of data, but the difference is that if we grow these data sets carefully, then they've got a better chance of yielding important insights to the analyst and to the decision maker. All right, so let's look at the timeline a little bit. In changing this to a data farmer's timeline, I'm going to look at these 225 years of love, luck, and tradition, and we'll change that a bit. I'm going to start with 239 years. So in my view, the roots of data farming have been around longer than the old Farmer's Almanac. And I'm going to keep the love. And the love is there. This is a quote that I really like. To love what you do and feel that it matters, how could anything be more fun? And I think that that is one thing that has sustained this community. We have a lot of people doing a variety of wonderful things. They love what they do, and they feel that it matters. So this is something that has been there from the beginning. I'm going to change the second word from luck to chance. And I'm starting this back at 1777 with the Comte de BUFFON, who is a prolific writer. In fact, in the over 600-page fourth supplement to his master opus, he has a section on an essay on moral arithmetic, where as a part of that, he talks about an experiment to go ahead and estimate pi by throwing needles on a floor that's marked with parallel lines. And this is just one idea or one way that, that chance has been woven into the fabric, really, of the simulation community. We look at randomness, we don't ignore it, but we go ahead and see how might this be used to our advantage. What is the variation in the real world? Leaping ahead to the 1920s, here's another way of looking at chance. Sir RONALD FISHER, who's really the founder of modern statistics, developer of the first hypothesis tests, has this interesting quote here where he says that nature will best respond to a logical and carefully thought out questionnaire rather than, as it says up front, a single question at a time. If we ask nature a single question, she'll often refuse to answer until some other topic has been discussed. And a couple of his seminal works there, a book on statistical methods for research workers in 1925, followed by his Design of Experiments book in 1935. And the idea here is very simple. And those of you that have ever seen one of my tutorials will recognize these next slides, but it's an important concept for our simulation community. And that is when we're looking at studying a system, and we're trying to think how to do that, there are different ways that people have approached it. So sometimes we might go ahead and say, let's figure out a base case. Let's look at our core simulation that we're trying to model. And then let's think of a few other excursions that are interesting, maybe an optimistic and a pessimistic scenario, or maybe a handful of ideas that people have on what might make a better world. And alternatively, we often see systems where we've got a simulation model built, and then the analysts may go ahead and change some of those inputs one at a time to try to get some insight into the sensitivity of the model to some of those underlying factors that could be changed. And this is not what I want you to do in a data farming environment. Like Sir Ronald Fisher, I want you to think carefully about exploring more than one thing at a time. And you can do that using designed experiments. A design is very simply just a table or a matrix where every column is a factor and every row is a design point that will tell you the combinations of those factor levels that you want to choose. And it's important to go ahead and study them together. Here's a very simple capture the flag example that we like to use in the Seed Center. If you've got kids playing a game of capture the flag, you're simulating that game. And there are only two things that you're going to vary in your simulation model. Something to do with speed and something to do with stealth. That red square may represent a bad outcome. So maybe that's a small probability of winning the game for the team of your choice. And the green represents a good outcome. But when we look at something like this, we cannot tell what is more important. Is it speed? Is it stealth? Or is it both together that are needed to get that win in the upper right-hand corner? And similarly, if we went ahead and did that one at a time variation, then it doesn't matter. If we increase speed, it might look like there's nothing to be gained. And if we increase stealth, it may look like there's nothing to be gained. And so we can't detect any interactions. We can't find that sweet spot, that synergistic spot, where we get a win. When we put them all together, we know that there is success. And if we've got numbers here instead of colors, and we've got a statistical software package, we can actually numerically estimate those effects. Or we can simply look at them qualitatively. How rapidly do we get increases due to these factors? So that's just a very simple example of a very basic design of experiments. And this is what Fisher was looking at. Developing the methods, developing the theory to go ahead and support physical experimentation. So he was looking at questions that I will say, what is? Trying to describe the world, trying to figure out how the world behaves, and trying to do that by thinking of more than one concept, more than one question at a time. So the graph on the plot on the right is just a notional picture of how I view different types of experiments that people might want to conduct. So on the vertical axis, we've got the number of factors, and that can range from few all the way up to many. And on the horizontal axis, we've got the complexity of the response. And on the left, it can be very simple. So we can be looking at simple linear models, linear relationships between the inputs and the outputs. We may be making many assumptions in order to let that happen. We may be making assumptions about the error distribution. We may be making all sorts of other assumptions. And over on the right, we've got high complexity. So we have a system that behaves in very complicated ways. So if we're really to understand that system, we're going to, we may have to do things differently. Now I want to move ahead to the third word in the timeline, transformation. The simulation community has many proud traditions as well, but I think that one thing that's been true from the beginning is that we've always been a community where change is necessary. And we're continually transforming the methods that we use. We're taking advantage of the new technologies. We're moving into new fields to go ahead and do the analysis. And in the 1940s, in World War II, there was a real sea change in terms of simulation and moving from these physical experiments into a new age. When World War II broke out, there were many in the US, also in France. They had a number of organizations where the computers were women, often the wives of scientists working on, say, the Manhattan Project or other defense-related projects. And this was a way that complex mathematical calculations got carried out. We really had rooms full of people doing redundant type calculations, very carefully trying to go ahead and solve equations that were impossible for one person to do or on their own. Draft of a description of the EDVAC by John van Neumann, which I think eventually ended up, the first computer was actually called the ENIAC by the time it was built. But in his draft paper discussing how this computing machine should be set up, it's interesting to go back and read it. So he does say that it's going to require a memory with a capacity of about 250,000 units! Exclamation mark. We look at that today, that's 32K of memory in your computer. He did mention that sorting problems and certain statistical experiments, and again, I'm looking at experimentation, for which a very high-speed device offers interesting opportunities. Today, we've got over 1 trillion-fold times the speed of those early computers. So if we had interesting opportunities back in the 1940s, just imagine what kind of interesting opportunities we have today. So it's really astounding, I think, when you look back and see how rapidly things have changed. Now, I mentioned gardening. Part of my gardening here is going to be pest control. So once the first computer was built, 1947, Grace Murray Hopper's logbook shows that, this isn't the first computer, this is a few years later, but shows the first documented case of a computer bug. So this was actually a moth that she found in the computer, taped it to her logbook, and there we go. Be nice to say that was the only computer bug ever found, but you know, it's amazing how often you kick that machine and a lot of them come swarming out. All right, so I want to look ahead a little farther. Winter Simulation Conference. Not quite today in history, about a month earlier, was the first conference on applications of simulation using the General Purpose Simulation System, or GPSS. And this later became known as the first Winter Simulation Conference, even though the name didn't officially become that until 1971. This was held in New York. Very much like today, it was a chance for people from different walks of life to get together and talk about what could be done with this new capability. So academics, researchers, industry, and so forth. Today in history, I was also thinking big, not in the context of simulation, but hey, what did I want to do next? I'll tell you, I wasn't thinking at that point that you know, in 2016, I'd be giving a talk on data farming at the Winter Simulation Conference. The first proceeding showed up in December 1968, and even from the beginning, there was a section on statistical considerations and also some talks on experiments and design. And those both included design in terms of describing different designs of experiments, but also in terms of design the process. So designing, a better manufacturing system, designing a better tool, designing a better procedure. So let's go back and think about our simulation analysis. And the statistics, the basic fundamental scientific experiments, I like to start with this idea of what is. We're looking at simulation, we're looking at experiments as a way of trying to find out what the world is really like. And from there, it's a very short step to start asking what-if questions. What if something changes? In the farming environment, what if we do change our watering cycle or our crop rotation or something of that sort? And a step further would be what matters. So again, we're not just looking at, say, a handful of alternatives like to capture the flag. What if we were faster and stealthier? But we're going ahead and trying to tease out what really matters in the context of doing these experiments. From there, I'd like to look and say what could be in the world, what should be, and how do we go and get there. And in this context, I've drawn the arrow because I think that we as a community have been and should continue to be thinking big. Now, after winter simulation, in the next years, there are a whole host of other questions that can be asked while you're looking at simulation models. Is my model working properly? What data should I get? Are there robust solutions? What's the risk associated with a particular alternative? What the heck was that? When you get a surprising result. What should we explore next? We found out something about our model. As we learned from the keynote speaker, what do other models say? Can we find commonalities or differences between those? And a question that's really important to us in the military, and I know to many others, how soon do you need an answer? So these are other things that we need to answer in the course of our studies. And when we look at that, in the context of big problems, we see that simulation is a different world. So going back to that notional graph, few to many factors, simple to complex responses, we see that we need methods for being able to explore things that inhabit that top in the top right corner. So we want to be looking for cases where there are many factors. We want to be looking for cases where there are minimal assumptions, so we can really find out what's going on underneath the hood. And I just have to, yeah. So my puzzle of the day is Sudoku. Sudoku represents a very special kind of space-filling design. If we're thinking of this in terms of setting values for factors, each column is going to represent a factor level or a particular factor. The rows represents the design points or the combinations of things that we're going to look at. And we find that, that this has some nice properties. If you play Sudoku, you can tell if you've got a good board or not. The goal here is to try to get each, the digits, in this case 1 through 9, showing up in each column, in each row, and in each square. And that's got some special properties that make it nice to go ahead and pull out answers. And there are a number of space-filling designs that people can look at. The important thing, again, if we're looking at a problem that's got a very simple response, we can get away with a simple design, like the one on the left. But if we're looking at a model that's more complicated, we want to be able to do trade-off analyses on what happens in the middle of that design space, then we need to start moving to things that look more like the ones on the right. So this is a very small case where I've got pairwise projections of the factor levels for 4 factors at a time in each of these subplots. But actually, we're interested in problems that are much larger. We regularly, with our students at NPS, have them run experiments on things that may be involving 50 to 150 factors. We've got some designs that we've worked on already, so we're prepared to look at things that are larger. But there's a need. There's a continued need for new designs and new analysis techniques that are suitable for exploring even more complex systems. Back to pest control. One reason that data farming is useful is that unless we experiment with a lot of things simultaneously, it might be harder to find some of these bugs. So I've got just a few examples of some things over the years. On the top left is a case where there was an input to a simulation model that was mistakenly not hooked up to anything inside it. And so going ahead and changing the values didn't have any effect on the output. That was an interesting thing to find out, and that popped out even though this was in a study involving not just that one, but involving many different factors simultaneously. In the middle, these red zigzag lines was another case of a model where we were looking at agents moving around in the sandbox. And the models had initially been, the modeling platform had been initially developed for only one type of agent, but then it was expanded to look at those that could move faster. And interestingly enough, there was a little error in terms of how that movement algorithm was used. And if we had studied it just at a couple levels, maybe just at the points where the red zigzag hits the blue line, we wouldn't have realized there was anything going on with our model. But by exploring it at lots of levels, we were able to identify this and have it fixed. And the one on the bottom right is a case where we go ahead and see that there's an overall trend generally downwards, except that first initial point is something that looks quite different. And again, this was a boundary condition. It wasn't working quite as it should in the model. But it wouldn't have been something that we would identify if we only did, say, a sample at the low and the high point. So what I want to say here is just the idea that, again, there are many ways that data farming can be helpful, but going ahead and doing that debugging is very good. If we find something that's wrong and repair the model, that helps with model verification. If we look at it and decide the model is coded correctly, but it's not behaving the way it should be, that will assist us in model validation. And if it turns out that we have to correct the intuition, either our intuition or that of the decision maker, then that's the case where our simulation model is helping support decisions that are different than those that would just be made off the top of somebody's head. So that's a very good situation. I want to back up a little bit because I forgot to mention in this context when we're thinking big, that in this time with the winter sim community and the larger simulation community, there were tremendous advances made in a variety of different areas. When we look at the idea of chance, all the advances that have been made in random number generation, for example, are helping us do a better job of modeling uncertainty within our models. When we look at Russell Chang and Jack Kleinen and their early work on design of experiments, that was very, very helpful in going ahead and setting the stage for simulation to become a more rigorous field. We look at the selection and ranking brought in by Dave Goldsman and Barry Nelson and many others. Again, a movement towards saying let's look at small problems that might be very narrowly defined to increasingly looking at larger problems in order to be able to address something of interest to the real world. So too many to mention, but this has been one of the things that I have really admired about the simulation community is the number and the diversity of the topics that have developed over the years. Skip back. Bear with me while I go through here again. All right. So I'm going to go back to a more personal level now, a data farmer's journey. I grew up in Ann Arbor, Michigan, and headed all the way across town to get my bachelor's in industrial and operations engineering. And I chose that field because they offered pizza at the orientation session. And when I went there, they had fascinating problems. They had 5 people get up. They talked about scheduling things in hospitals. They talked about logistics. They talked about waste management. They talked about criminal justice. They talked about a paradox in one machine scheduling. And it just looked like a lot of fun. I headed off to Cornell University, where I got my MS and PhD, working with Bob Beckhofer, a gentleman and a scholar in the selection and ranking realm, where I worked on contributions to the Bernoulli selection problem. Years later, I think I might have reworded that a little different so it didn't sound like I was making this a bigger problem. But anyway, at Cornell, I also met and married Paul Sanchez, my favorite simulator, my favorite co-author, and the person most responsible for bringing me into the simulation field. So special thanks. After Cornell, we headed to University of Arizona, the College of Business and Public Administration. And here, I worked on a variety of different applications. I should say that the Bernoulli selection problem, one reason that attracted me to that in grad school was the idea that it might be useful for clinical trials. And it didn't end up having the same immediate payoff that way, but as I said, others took this selection and ranking idea to simulation, and it's become a very important topic in our community. At Arizona, I did, however, keep working in healthcare. And together with Doug Hooley and John Christensen and some others at the University of Arizona, we did studies of health maintenance organization foundations and failures. We looked at how the industry shared information when it was in its infancy stages, and then later ended up converting from a cooperative type growth of the industry to a point in time where that information now became something of competitive advantage to the initial companies. So anyway, this was a case where big data, lots of data sets, complicated models, trying to pull in the different demographics of the different states, the different types of responses they might have to HMO foundings and failures, and so forth. I was also doing a little work looking at design of experiments for manufacturing, and ended up coming back to WinterSim in 1991, where I gave my first talk at WSC on robust design for simulation. And again, that's the point, kind of I never came back. But the idea there is that when we're looking at uncertainty, there are different ways of thinking about that uncertainty. And one is that it's a nuisance. It's something that you should try to minimize or get rid of. Control, screen out. And the robust design idea says there are going to be cases where there is uncertainty in the real world. You want to be able to have a system that's going to respond well despite that. So the graph on the lower left, the red bars there are simply trying to show that In some cases, if you vary the inputs a little bit, you'll get dramatic changes in the output. And in some cases, if you vary them a little bit, that output will be relatively stable. So this is something to consider in many cases as part of our design process. And I think it's important in the context that it, again, goes along with trying not to make too many assumptions about the way the world works. If there is variability that you're not going to be able to control, you want your system to be able to handle that or respond to that in a good manner. You can't just assume it away. I headed on to University of Missouri, St. Louis, still in a business school. Had the chance there to work on a large-scale model that forecasted risk and reserve levels that were needed for foreclosures on home mortgages for a top 10 financial institution. And this was back in the early 1990s. This was not right before the crash. I am proud to say that this particular institution did not need a bailout in 2008. I don't know how long they kept using our system, but we do know that they used it for several years to go ahead and start, assessing the risk associated with different pools of these mortgages that they would sell or swap off. So again, another big data set, another complicated model, an eye-opening experience for me because I thought banks would have very accurate data, and it was amazing how much was different when they had 3 different systems tracking 3 different things. And amazing just how many people in the United States seem to have the Social Security number 999999999. And then out to Naval Postgraduate School for what we thought was a 1-year sabbatical. Ended up staying. The students are fantastic. The problems are really, really interesting. And this is a place where there just are great opportunities to be able to make a difference in policy in the very short term, particularly working through our students. While I was out there, Tom Lucas and I founded the Seed Center for Data Farming. This grew out of an early grant that we got from the Marine Corps' Project Albert, which was looking at trying to set up a group of methods to go ahead and incorporate some of these new modeling platforms like agent-based models, going ahead and looking at different analysis and visualization techniques, leveraging some of the new high-performance computers that were coming online, and working closely with subject matter experts. That grew into work that we did for a number of years with NATO, and got a chance to work with analysts and subject matter experts from around the world on that. So it was a very exciting time, and that NATO group still continues. The first paper in Winter Sim that mentions data farming is back in 1999 with Gary Horn. And when I Googled yesterday on the website, we've had over 40 papers that go ahead and show the word data farming. So the ideas are out there, and that's very gratifying. If I look at a view of the Seed Center from a distance, what we've tried to do within the Seed Center is say we're going to start with a problem. We're going to go ahead and put together a team to help analyze it, have them come up with and build a model. That can take varying amounts of time depending on what the situation is. But then design and run experiments on that model, analyze the results, see what insights are drawn from those, and iterate around until we get to a solution. And a big part here as well is the glue to hold it together. So there are lots of good models out there. There are lots of good designs out there. There are many good analysis and visualization packages. And what has been the bottleneck on some of these complicated problems has really been the analyst. If the analyst is the one that has to sit there and push the button to go ahead and keep generating the results, or manually enter new levels for the factors. So that's what we've tried to do with the glue, to ease that process. And at NPS, we've been doing this to try to ensure that our those in uniform have what they need to accomplish their missions. We've worked on a large variety of problems, military operations, but a lot of things as well. So we're not just, humanitarian assistance and disaster relief are quite important. Energy is becoming increasingly important, alternative energy. We've got protecting critical infrastructure, going ahead and modeling social dynamics. So we've looked at a wide variety of topics over the years. Our students in particular have looked at a wide variety of topics. Our overall goal has been to try to make modeling and simulation more effective for decision makers. And our philosophy on that is that it's time to have the model work for you. When we think about many simulation studies, there's a lot of effort that goes into the modeling and development phase, from the conceptual model up through coding, up through debugging, and so forth. And often there's just a small amount of time left at the end to go ahead and do some analysis. But once you have that model, and particularly if you've built that model from the beginning to be able to go ahead and make it easy to do these large-scale explorations, that's a great time to let that model work for you. You might have to give, your initial answer, your initial study is due next week. Report the results you have. But there's no reason you couldn't explore that model further and get broader and deeper insights. So, predictions. Predictions aren't always easy. When we look at the next stages, again, I want you to be thinking big, but thinking big not just in analysis, but what are going to be the next challenges when we look at the theory of simulation, the different methods we use to apply to that, the software that we need to be able to go ahead and instantiate our models, and the applications that we're going to look at. Whole host of things. We've got big problems facing the world. We've got many people at this very conference that are working on these problems, and they're important. There's room for more. And so I would like to encourage you to think about how your work can contribute in some way to addressing some of these problems. This is a quote that we found in the Nobel Museum, which I'm looking forward to visiting in a few years again, perhaps, when WSC goes to Sweden. And to paraphrase this, we can think of every scientific discovery going through 3 stages. And the first is, that's not the way it should be done. Okay, that's not the orthodoxy. And when simulation first got started, there were a lot of instances where people said that's not the way things should be done. We've got equations now that we can solve numerically on a computer in seconds or even faster, where the error due to the random or pseudo-random numbers is less than the width of the line that we can use to plot the results. And so it shouldn't matter whether that's a computational or an analytical solution. The second stage, it's been done before, nothing's new. And the third stage is, that's the way it's always been done. I would like to see that years from now, maybe not too many years, maybe just a few years, that there's a much larger proportion of software, of projects, of studies, where people have been able to quickly and easily do some sort of large-scale designed experiment. That can be a massive sensitivity analysis, just to go ahead and try to make sure that that model is working appropriately, try to get a better sense of the variation in the outputs that they might see if there are just tiny changes in those inputs. Or it might be a much more in-depth dive down to try to find out what are the key drivers of this complex model, and how might we use those to affect public policy or affect important decisions in other domains. So, question of the day. What should simulation be and do in the future? And I want to try something a little different here. I do it in my classes, but I haven't done it in a room this large. So in just a minute, well, I'm going to start by having you think for 10 seconds about what you think simulation should be or do in the future. And now I'd like you to turn to your neighbor and take half a minute and share your thoughts. Okay. Never doubt that a small group of thoughtful, committed citizens can change the world. And the Winter Simulation Conference, we are part of a community, not just of our countries, but of the global simulation community. The networking, the collaboration that we can do, I think has great potential. So what should simulation be and do? Oops. I thought I had these all right. I think I clicked too fast. What should simulation be and do? And how can we make that happen? So that's my challenge to you. If I go back and look at our Data Farmers Almanac, I've tried to give you forecasts, a little bit of a bird's eye view, some food for thought, some questions and some quotes. If you're new to the simulation community, as I was once, as we all were once, come along. It'll be a great trip. I didn't talk in detail about any of the many successful projects that we've had, but I would like to say we've got lots of information available on our website, harvest.nps.edu. So if you want either more technical details about some of the methods, or you want application examples of some of the success stories, you can go ahead and look there. And I'd finally like to say thanks. So thanks to you. Thanks to all those and all the others that have helped work and make this such a vibrant and welcoming community. That's all.
So we have time for some questions. There's a microphone up front here. If you have a question, I'll bring the microphone to you. Just raise your hand and let's use up the last time.
Yes, one of the things that, we haven't given a lot of consideration, some more recently on inputs. The sensitivity, we don't estimate inputs very well in many cases. We spend a lot of time talking about validation of models. So how do you see your field of design experiments and so forth? How could we apply that to really help us improve the effects of inputs?
So one way I think that the data farming experiments can be useful is that we can now view those input distributions as themselves factors. So even if we don't have good data available, or there might not be data available, perhaps we're looking at some future type system, we can change the distributions in terms of their shape and their form. We can change the parameters of the distributions when we go ahead and run the experiment. And if you change them over what you think are reasonable ranges for the decision maker or for the subject matter expert, and that doesn't lead to drastically different results, then that tells you you've gotten enough fidelity in that part of the model. And so it might help you focus your data collection efforts on those things that really matter.
I expected a little bit more data from this presentation, so I was, I have to admit, positively surprised, because I think that as a community, in particular here, for 50 years we are building models. Don't you think it's time that we start to develop from data farmers into model farmers and try to move up from the data to the information to the knowledge and wisdom level? Is this something which you foresee as well?
I think definitely that the models are for thinking. That's another quote that we like to use. And so yes, we do need to get to that next level. Part of the complexity that we're seeing in many of the areas that we're looking at these days is that there are multiple models, there are hierarchies of models where information from one flows upward to the others, but not necessarily in a clean or one-to-one type transformation. So yes, I think this is another area that's ripe for work. Another thing on the methodology standpoint, a lot of the techniques that are developed are focusing on a single output measure. And again, in the problems that we see, whether it's healthcare, whether it's military operations, whether it's supply chain and so forth, we're generally going to have multiple performance measures. So that's another area where we're going to have to do a better job of synthesizing different types of data and different sources of data to really move ahead.
Thank you. Susan, in terms of harris.nps.edu, would you comment on one or maybe a couple of the applications there that you find especially useful and interesting?
We have a couple of papers highlighted at the top of our website. So for those new to it, that can go ahead and perhaps look at those applications. One example that we're very proud of, it's a bit older now, but we had a student, Chris Nanini, who did a study with the U.S. Army when they were going ahead and trying to decide how many unmanned aerial vehicles, how many classes of UAVs they were going to have in their future forces. And this was part of a very large, complex, dynamic retasking simulation. These UAVs were going out for surveillance. The results of Chris's study were part of a larger study that was credited with saving the U.S. Army over $20 billion because they decided they didn't need 5 classes as they had planned. They could go ahead and only start the procurement process for 3 classes. So that's one success story that we're very proud of. Not all of our students have that. So there's one example. Another interesting area, I'll say it's early days yet, but we We had some students looking at humanitarian assistance and disaster relief operations. And they actually farmed not a simulation model, but they farmed a stochastic optimization model. And this was a structure that had been put together, had been written up in some papers. And by doing some more variation of some of those many coefficients that are hardwired into the stochastic optimization model, what popped out is that there were multiple optimal solutions. And so in fact, GAMS and CPLEX, which I found out later by talking with my optimization colleagues, would stop the first time it found a feasible solution, and that tended to be a very high-cost solution. So the results that had come out of earlier studies were suggesting that the best way forward was to invest a lot up front in pre-positioning some of these disaster relief resources. And as I say, sort of first step, but on the one study that we looked at, it looked like you might be able to do just as well if you were more agile and responsive to those disaster efforts without expending the money up front. And if that holds up with further studies, that's got important implications for how the Navy and the Marines, who are often on the front lines of these relief efforts for hurricanes and tsunamis, should go ahead and approach the problem.
Susan, you've had projects that were conducted for military sponsors and projects conducted for civilian sponsors. Do you feel comfortable in addressing the question, when you made the reports of results to the sponsors, did you see any differences in whether they were operating in the military domain or in the civilian domain?
I hadn't thought of that before. I'll say one thing that's common in both cases is it's important to really understand what the problem is, and to do that you need communication with those that are having the decision not just at the end, but at multiple points throughout the process. So the home mortgage example that I talked about, one thing I loved about that study, at the time it was taking on our campus machines about 14 hours to do one of these runs. And the client would call up and say, would you change the unemployment rate in year 4 in this state and rerun the model and see what it says? And we would generate a whole new set of reports. And they kept telling us, it's not quite right, it's not quite what we want. So running the large data set where we were able to say, we're not going to bother running it unless the changes are more than this amount. We can show you that it's going to be decimal dust in the changes. But the other is we finally put in what we called a George factor. One of their chief economists, very smart guy, said, these reports just don't look quite right to me. I think you're overestimating the amount, or underestimating, I don't remember which, the amount of time on the books. So I want to have a multiplier to be able to adjust that. We said we can do that, but that's going to change everything else about the model. But if there really is something we're missing that's important in the real world, we will do that. So he put in the multiplier, he went off to estimate it, and he came back 2 weeks later and said, my multiplier is 1. And when we ended up then rolling the system out and finding that the changes that it was predicting were coming to fruition in the quarter following that, it was picking up on things that these very smart people hadn't been able to pick up on before. That was important. One of the big challenges in the military, I think, is the timing. We just have many cases where we had that short amount of time. One thing we have found is that it's always good to ask the sponsor what they expect. Because if not, it's very easy to say, here's the report of my study, I've done a careful analysis, and they say, that's so obvious, why did I need simulation? I knew that ahead of time. So I think checking to make sure that we are finding out what the intuition is, what the knowledge is about a problem when we start it, makes us better able to assess what the simulation is doing to either support or modify or refute that intuition is important.
Okay, it's 12:20. I'd like to again thank Susan Sanchez for her great talk, and everybody else enjoy the rest of the conference.
Actually, Susan, I had one question about one of the slides there. Is it true that it's your birthday today?
Yes, it is.
It is. Happy birthday.
Thank you.